Hello everyone, myself Prashant. Topic for today is the abridgment of the VLSI. At the end of this presentation or video, one can have an idea of what is VLSI and what are the various steps involved in order to develop an integrated circuit. What are the various kinds of transistors which we can use or which we have been using in an integrated circuit, and some of the case studies related to VLSI and the job opportunities for a person who choose VLSI as his or her career. Let's move forward without any delay. Following are the topics covered as part of this presentation. What is VLSI? Evolution of various transistors used in the VLSI. The basic ASIC flow, and the role or importance of a physical design engineer. So at this point of time, I would like to say that I am a physical design engineer who is in the industry for the past 7 years. Okay. The latest trends in the lower technology node, which we are following, some of the case studies and the job opportunities at the end. What is VLSI? So VLSI is an acronym for very large scale integration. VLSI is an acronym for very large scale integration. So one will be developing an integrated circuit. So as part of the VLSI, one will be developing an integrated circuit. So if any of the audience is from the electronics background, so you might be having an idea of a circuit. So basically IC integrated circuit is like different components soldered together in order to achieve some functionality. So if you might have remembered in the electronics labs, like in the digital logic designing lab, you might have designed the clippers and clampers. You might have used several transistors and resistors or capacitors. You might have put it on the breadboard and in order to achieve one functionality. So it's like I can say this is one kind of integrated circuit. So not only that, so the one which we are using in our mobile processors or in your laptops or any electronic gadgets. So that is nothing but the processor. The processor is nothing but an integrated circuit. So I can say like we'll have both active and passive elements in an integrated circuit. So some of the active elements like bipolar junction transistors, CMOS, and some of the other transistors which we have. So we can call them as an active elements, and the passive elements like the diodes, capacitors, and resistors. So these two together will form a circuit, and we call it as an integrated circuit. So, but I'm saying that both, whatever you have developed as part of your lab or digital logic designing lab, the clippers or clamper circuit, and also whatever the processor we have is both of them are an integrated circuit. But what decides what is the basic difference between these two things? So I can say that the complexity decides the type of the integrated circuits we have. So we have some of the types of integrated circuits. So the first one being SSI, it's small scale integration. If at all we are having 10 to hundreds of transistors in our circuit, so we call it as a small scale integration. So next one is MSI or medium scale integration. If at all we are having some hundreds to thousands of the transistors in our design, we call it as MSI or medium scale integration. And then coming to LSI, the large scale integration. So if at all we are having greater than 10,000 of transistors in our design, we call it as an LSI circuit. And then our focus VLSI, very large scale integration. If at all our chip or a circuit is having around 1 million of transistor or more than that, we call it as a VLSI. The typical chip will be having like more than 1 million of transistors in the current designs. So whatever it may be, it can be artificial intelligence chips or any graphic processor or SoC or anything. So it will be having like more than 1 million of transistors inside that. So BJT, CMOS in our integrator circuits. So BJT, bipolar junction transistor, you all know that it is a current control device. So basically BJT offers high speed, more gain and low output resistance. So whenever we wanted to achieve a functionality where performance is the most priority, so we can just opt for the BJT. So but it has its own limitations too. So basically we will be using this BJTs mostly as part of my analog devices or analog designs. And then CMOS. So CMOS offers high input resistance and better for low power logic gates. So in our digital world and in our digital designs, we'll be using this CMOS. So because of its own advantages, we'll be using this CMOS things inside it. Okay, let's move on to the next one. Evaluation of various transistors we have used or we have been using so far. So let's start with the planar CMOS. So planar CMOS, so you can see on the screen how it is looking like. It's on one side you're having the source and the other side you're having the drain, and on the top you're having the gate. So you know CMOS is the voltage control device. Whenever you apply some potential to the gate, the channel will be formed underneath that in between source and drain, and it enables transfer of electrons from the source to drain, and that's where we call it as the switch is on. CMOS is acting as a switch here, and switch is on, and it is uh, like we can see the output now. So when we apply some potential and that potential to the gate, when that potential is greater than the threshold voltage, only then we can say the channel is formed underneath that and the transfer of electrons is happening. So I'm saying that it is a horizontal channel here. The planar CMOS is having the horizontal channel. So horizontal channel in the sense the source and drain are at the same level and the gate is above that. So as I said to you, the gate or the CMOS is a voltage control device. So we are having we are applying the potential to the gate, and it's like the formation of the channel is only controlled from one dimension, so which is nothing but the from the top. So that means from the top, based upon the voltage which is applied to that, the channel will form, and so that's why we say that the control is from only one dimension. So earlier ICs, most of the earlier ICs are made up of the planar CMOS. So but what happens as the technology node is shrinking? Okay, so for the some of the guys who is new to this, so I can say that based upon the channel length, we will say we will decide which technology node it is. So you might have seen like 180 nanometer to 50 nanometer technology nodes also. So that means 180 nanometer to 50 nanometer is nothing but the channel length which we have. So the channel length, based upon the channel length, we say the technology node. So that means if the technology node is shrinking, the channel length is reducing. So when the channel length is reducing, the area which my gate is going to cover is going to reduce. That means it is nothing but we are having kind of limited controllability over the formation of the channels, because the technology node is shrinking. The I mean, so how well or how faster we can prepare, or I mean the how amount of controllability which we have here is reducing. So that's why it happened to move to the next uh, type of design or next type of transistor. So we'll see what it is. So FDSOI. So it's nothing but fully depleted silicon on insulator. So once again it is a horizontal channel. So but what is the difference between planar CMOS and FDSO technology is, so the construction part is different. So as you can see here, we are having kind of ultra thin buried oxide layer here. So we call it as buried oxide because it is underneath the source and drain. So we'll be fabricating this ultra thin buried oxide layer first, and then on top of that we'll be growing the source and drain, and then oxide layer, again one more gate. So the channel which we have here is very thin. So when you compare to the planar CMOS, the channel which is present over here is very thin. So and as the channel is very thin, we don't even need to have or add any kind of doping, any kind of, we don't need to do any doping to the channel, and so that's why we'll call it as it's fully depleted. So that's the reason we call it as fully depleted silicon on insulator. So as I said, the transistor structure won't change, but a thick layer of insulator will be added below the channel. So we have some buried oxide layer present over here underneath that. So that's the only basic difference between that one and this. So leakage will be very less compared to the planar CMOS. So why the leakage is less? So for example, we don't have the planar CMOS. I'm kind of drawing the CMOS how it looks like. So the cross-sectional view of the planar CMOS can look like this. So whenever the channel is formed, so we will have the kind of electron transfer, or the channel is formed and the electron starts flowing. So they can take any path over here. So it can go from here to here, here to here, and also some of the leakage will happen like this. So channel is formed and some of them can even go like this. So now because of this we can say the leakage which we have in the planar CMOS is kind of more. But now as part of the FDSOI, as thanks to the buried oxide layer which we have, we will not see such kind of leakage happening over here. So whatever may be the transfer we have, it will be above this buried oxide. So you can see we have here oxide on the top and oxide on the bottom. So I can say now we kind of have a backgate formed here. So one being from the top and the backgate here is from the bottom. So we have oxide and above that source and drain. So it has one kind of advantage, I can say. So I can say it have better control over body bias and is dynamic. So I would like to explain what it means. So body bias. So first of all, I want to explain what is body biasing. So we have the substrate over here underneath here. So this dark gray color is the substrate. So we will be kind of applying some potential to the substrate, and we call it as a body bias. So substrate is nothing but the body, and body bias or some voltage will be applied to this. So as we have the alkaline buried oxide layer, so body bias plays a significant role, a prominent role over here. So we will be kind of say we'll be having some potential applied over here. So we'll be having some potential applied over here, and it will be connected to my body bias, the body. So now based upon this body bias or body bias voltage, so we can say we can alter the VTH over here. So that means we have kind of better control over the body bias. Not only that, so it is dynamic. So once the chip is fabricated also, we can alter this body bias voltage, and we can achieve, we can operate our chip in the two different modes. So as the body bias can be altered and it is also dynamic, so we can operate. So based upon this body bias, we can say the threshold voltage is kind of varied, or we can alter the threshold voltage over here. So as the VTH can be altered, I can say, okay, before this, so how the VTH can be altered, because like say, the voltage is the potential difference between two different plates. So now here, these two are kind of say like acting as a plate over here. So you have the body bias applied over here, and so I can say the VTH can be altered. So what are the two different kind of operations possible? The one being more energy efficient and the other being more performance. So based upon the kind of threshold voltage we have, if it is high, one kind of operation, and if it is low, other kind of operation is possible. But we kind of have similar things possible with the planar CMOS also. So where we are kind of changing the doping concentration, and we have two different types of cells, so which are nothing but low voltage, high voltage, or medium voltage, medium threshold voltage. So low threshold voltage or medium threshold voltage or high threshold voltage we have. So but here the kind of operation which we can achieve is dynamic, so because it's runtime. So once it is fabricated also, we can kind of change it, and we can use it as per our requirement. So that's why I call it as, I have used the word dynamic here. Okay. Yeah, but because of its challenge, because of the complexity related to the fabrication steps which we have, so it is, it was not, it hasn't become much popular. So ST Micro is the first one who kind of developed this kind of technology node, and then so it was not encouraged, or it was not being used more across all the designs. So we kind of developed a new technology, new kind of transistor, so in order to overcome whatever may be the challenges which we are facing before. So let's see what it is. So it is nothing but FinFET. So field effect transistor. So I have put like planar CMOS and the FinFET side by side. You can kind of correlate what is the basic difference between. So both of them are like cross-sectional views which you have. So the planar CMOS is the horizontal one, horizontal channel, as I said to you. But here you see, it's kind of embossed, these dark gray color are the source and drain things. So it's kind of embossed, and from we have source on one side and the drain on the other side here. So but here the basic difference, or the major difference over here, is the gate. So the gate over here is now 3D, so that means it's three-dimensional one. So from the left, right, and top, we can kind of control the formation of the gate. So whereas in the planar CMOS, the control is only from the one direction, that is from the top. So but here in the FinFET, the control is from the three dimensions, which is from left, right, and top. That means we kind of have more or better controllability compared to my planar CMOS. So with this, we kind of increase the controllability which we have in the 3D gate architecture of FinFET. We can increase the controllability of the formation of the gate. So it has high drive currents, by the way. FinFET will have high drive currents compared to my planar CMOS. So it has faster switching times also. So the next one, or the next kind of transistor, is GAA, which is nothing but gate all around. So FinFET being with the FinFET we have a control from 3 dimensions, but in the GAA gate all around, we have gate in all the directions, from left, right, top, and bottom. We have the gate, and and now the fins are now nanowires. In the FinFET, we have the whatever the fins we have here they have become nanowires. So controllability is even greater than the FinFET. You can see the formation of the channel is even greater than the FinFET. So you can see here that in this diagram, so how the fins, the nanowires will look like. So here it's like 8 nanometer. So you can imagine how thin this particular thing is. So it's like it's very thin. The diameter of this is like 8 nanometer, and it's very thin, which we have over here. And the kind of the construction which we have over here is kind of very typical, and it will be like more it's like more burden on the process engineer, like it involves uh, in various complex processing steps or fabrication steps here. And we can say we don't know what is the yield which we have, which we can achieve over here. So this is about my gate all around. So let's move on to the next. Before that, so I can show you like all in one picture. So this is the planar CMOS, and it's the double gate FDSOI and the tri gate. So from the top left and right we have them, and here we can see the fins. Okay, and I can say based upon the number of fins we have, the performance will kind of increase, or the resistance will kind of increase. And then we have the gate all around. You can see the nanowires over here. So this is the gate all around and well fed. Okay, so all these whatever we have discussed so far is like everything in the one page we have. And at present we are kind of using the FinFET or the tri-gate architecture. So we are yet to realize this particular thing, and it has some of the complexities involved in that. Okay, so I would like to discuss some of the important fabrication steps as part of fabricating the integrator circuit at the foundry. So the first important step, or first important point here I want to discuss is crystal growth. So you all know the silica or the sand is the main ingredient in development of our integrated circuit. So we will take the silica, the pure form without any impurities, we'll heat them, we'll heat that at like with higher temperatures, we'll melt that, and we'll kind of form a cylinder or cylindrical shape, and we will then cut that cylindrical shapes into smaller sizes. So after that, so you can see a CD or a disc formed. So it will be just like our regular CD which you have at home. So it will be just like that, but so it is with completely with the help of the silica, and we will use this for developing or for fabricating the transistors in that. So overall, I can say like once that cylinder is formed, we will just divide, or we'll just cut into some pieces, and we'll just make use of each of that crystal. So one point here I want to mention about the crystal is, so larger the dimension or larger the diameter of the crystal, thicker it has to be in order to maintain or achieve, or in order to have good mechanical stability. So next is the oxidation. So oxide layer will be used several times or multiple times during the fabrication process, because it has some of the good properties, like so it is good for insulator. It has good insulating properties, it has good dielectric properties, and it has good mask properties. So I'll say what about what I mean by all of these in the next I mean next soon. So photolithography. So photolithography is like kind of passing the UV light and etching the unwanted area. So this is like photolithography. So at this point of time, I would like to discuss, or I would like to show how fabrication will happen. So let's suppose we wanted to fabricate one metal shape, so which is like this. Let's suppose we wanted to fabricate this, and in order to do this particular exercise, or in order to fabricate this particular metal shape, the first thing which we wanted to know or which we wanted to have is a mask for this. Let's say we are having a mask like this. So not only this, so as you want to fabricate this in the middle, let's say wherever we want to fabricate such shape, we will be creating a hole like this. So obviously we'll have the crystal in the bottom like this, and let's assume we have developed uh, the oxide layer on top of that. Let's suppose it is like this. So we will pass the UV light of certain frequency through this mask, and wherever it is passed or wherever it has gone through that particular mask, so I can say that particular area will become soft. So when that particular area will become soft, so and after we pass the required chemicals and etch this process or etch it, so we will see something like this. Okay, I think it is completely gone. I will draw again. So the remaining portion for us will be looking something like this. So the remaining portion which we have will be looking like this. So in this we will be having some empty area present over here. So in that area we can fill it with any metal or with any kind of material we wanted to. So after that, so that's how I can say, like we can kind of fabricate our required shapes, so with the help of the mask and with the help of the photolithography or oxidation process. So this is like one of the important steps in or these are some of the important steps during the fabrication. So it may not like give you complete idea of how the fabrication will happen, but it is like a glance of what is going to happen or what may happen inside my uh, fabrication process. Let's move on to the next topic. ASIC flow. So application specific integrated circuit flow. So I'll say this as application specific integrated circuit. So all the integrated circuits out there in the market, all of them or most of them will be application specific. That means, so we kind of develop or we kind of fabricate or integrate a circuit. So we will have some of the functionality in our mind, and then we will kind of jot down what are the requirements you need, and what is that required in order to achieve that functionality, or in order to have that specifications, in order to meet the specifications, and we kind of develop an integrated circuit. So the developed integrated circuit will is responsible for achieving one specific functionality. That's it. So it cannot have any other functionality on the fly. So that means, like, say you kind of say you have one particular functionality, and you have developed an ASIC, that means application specific integrated circuit. That's it. So it will be achieving that functionality alone. So let's say the graphic processor. So the main purpose of that is to provide it's for graphics. That's it. So that is its functionality. So that's why we can say it's application specific integrated circuit. So most of them out there in the market are application specific integrated circuits. So what are the steps involved? Let's see what are the steps involved here. So starting with the specifications. So the specifications, say the specifications. For example, let's take the case of any processor or any CPU. So what you need, so what are the basic specifications which you can have? it's like what is the how much is the RAM we have, how much is the cache memory we have, and how fast is the clock, what is the clocking speed in other way, in other words, or I can say how many USB ports it can support, and all these all these together we can say it's specifications. So these are some of the specifications, some part of the specifications I can say. Because and also what kind of protocols we need to use in order to communicate with peripherals, or in order to communicate from a processor to the peripherals. So all these kind of things will be deciding upfront. So that will be coming as part of specifications. Whatever I might have said is it's not complete. It's part of them. But yeah, so that's how the specifications will look like, or that is what I can say the specifications are. So then we'll jot down them and we'll make that as our requirement, or as our starting step, and then we'll go to the next step. So that is nothing but my architecture design. So in order to have all these specifications, what kind of architecture we need to use, so is the next one. So we can also say that what kind of processor do we need to use x86 or ARM core or anything. So what kind of cores we need to design it, how my architecture will look like in order to have this kind of functionality. It's like kind of block diagram which we can have. We'll develop or we'll decide here. So at this point of stage, or in this particular architecture design stage. So then coming to my RTL design. So now we have the architecture design, and based upon the specifications and architecture design, so we kind of start coding that. So we have front-end engineer, so logic design engineer we call them, and we will kind of use either Verilog or VHDL, and we start coding the language, or we start coding the design or functionality. So we kind of have these two inputs in our hand, and based upon the specifications and architecture design, we kind of start coding them. So here the RTL designer is, I cannot say it's like only one person who is going to design or who is going to code all these things. So it's not possible, or it kind of delays the process. So we will be dividing our work into some steps. So we'll be dividing our complete design into some subsections, and each subsections will be given or hand over to some of the front-end engineers, and each of them start working on them. So we kind of have a wrapper logic at the end of the day. Then the wrapper logic, we kind of wrap all these codes or all these logic together. So that means all some of the engineers together will start working on this, and he will be kind of achieving the functionality which we need. So that means we kind of have no logic in our hand, or after this particular RTL design step, we kind of say I can have one logic in our hand, so which is able to achieve our functionality. So, or at least I can say the designer thinks he has coded something which is similar to the specifications which he has. So but someone has to verify it, right? So that is what the step here, the RTL verification. He thinks that he has developed a code according to the specifications, but this particular guy, the RTL verification guy, he kind of identify, or he kind of verify, so whatever this RTL designer has designed is meeting or matching the specifications or not. So I can say some of the say we can have some uh, iterations possible over here. So RTL designer will come to RTL verification guy. He will verify. He can find out some of the bugs, and he can kind of give it to the front end person, RTL designer. Again, he kind of change that particular thing, and again he will be giving to verification. So some of the iterations might happen over here. So some of the iterations might happen over here, and at the end of this RTL verification stage, I can say, so one particular code which is developed and verified will be in our hand. So which meets, or which kind of meets our expectations or specifications. So this is what I can say. It's at this stage we have that one in our hand. So we kind of use UVM methodologies in order to test this, which is more prominent nowadays, UVM. And like say we kind of use various different kind of tools simulators to test or to verify the functionality over here. So the next one here is like kind of synthesis. So here synthesis. So far whatever maybe the things which we have is like completely logical. So at the synthesis step, at the synthesis stage, what happens is we kind of convert that logic into the gate level netlist. That means whatever maybe the functionality which we have, we will develop or we kind of implement that with the help of the normal regular gates like NAND gate, NOR, or muxes, or any kind of basic functional gates which we have. So we'll kind of develop our logic or convert our logic into our uh, gate level netlist. So at this step, so it is the responsibility of the designer such he has to design the code in such a way that we can convert all of his logic to the gate level netlist. So at this step, the synthesis guy can say that so some of the code which he has developed is if he can convert to the gate level netlist or not. So he'll kind of give the feedback, but most of the cases this RTL designer himself will check that, and he will give the constructs. He will write the code in such a way that it can be synthesizable. It is synthesizable. That means we can convert that code into the gate level netlist. So at this step, so at the synthesis step, we kind of have one gate level netlist. That means the logic is implemented in the help with the help of basic gates, and that is like kind of output of my synthesis stage. So then coming to my DFT, so design for testability. Okay, so here I just want to say you one kind of the motivation which I had, or why I have chosen this particular VLSI field. So back then, when I was in my engineering, I think I have a PC, and it kind of stopped working. So I just took that thing to my technician and I showed him. So he said that there is some problem in the processor, so you need to buy a new one. So I was surprised. Asked him, so just repair that and give it to me. He just laughed at me and said that so if the processor is gone, I cannot repair that. So I asked him, so why when everything can be repaired, why can't it be repaired? I asked him. So he again laughed. We cannot repair that. So this in this moment, I kind of developed like the enthusiasm or kind of it's like bugging me. So what is there inside that which it cannot be repaired? Why this person is saying this? So is he just bluffing, or he's just fooling me, or what? So I just kind of developed that kind of feel and started thinking more. What is this process, or what is this and everything? So back then we were like very small, and we don't even have. I think uh, even the VLSI subject was not introduced back then. So that's the moment, like say when I developed, I start digging more, and I kind of develop that enthusiasm or kind of feel towards this VLSI, and that's how I enter. So again, that's a different part of the story, but let's get back to the business. But here, the DFT, so design for testability. So this is the one step where the DFT engineer will add some kind of code into my design. So once the chip is fabricated, we can kind of test that particular chip. So that means, so the fabrication steps, or I mean whatever maybe the IC which is fabricated, so it has to be tested first. That means all these complex fabrication steps whichever we have, after this we cannot know, or we don't know, or we are not sure how my chip is going to work, or how many of the chips fabricated in the lot is working. So in order to test that, we kind of need to have a mechanism to test it. So that is how, or that is what my DFT is. So with the help of the DFT, we kind of test the chip. So if the chip which is fabricated is as per our expectations or not. So whatever we have designed, is if it is developed as it is, or is there any kind of mishaps in that. So if if that's there, so we can say like we can this DFT will enable that process, and we will test that chip once it's fabricated, and we will say yes, this is working and this is not working, this can be shipped to the customer, this cannot be. So that decides like yield of the design, also yield of the technology node also. That means like say we have, for example, say we have one complete die. In that die we can kind of develop some thousands of ICs. So out of the 1,000 in that lot, how many of the transistors are working? So if out of the 1,000, like 800 are working, we can say 80% of the yield we have. Or else, for example, say in that out of 1,000, all the 1,000 are not working. So it's a simple thing, right? That means something is wrong in the fabrication step itself. So that means now the fabrication engineer or the process engineer will kind of look into that and what has gone wrong, and he'll find out, and then only the process again the fabrication steps will resume. So that means like the DFT is plays a prominent role. So once the chip is fabricated, which one needs to be shipped to the customer, which shouldn't be, so will be kind of decided here. So and again, so that's thanks to the DFT engineer, he will be kind of adding some of the design logic into that to enable this process. So yeah, so that is about my DFT, or what is the functionality of the DFT guy. So after this step, the actual work of a PD engineer or physical design engineer will start. The physical design engineer is the person who will kind of realize the logic. So at this point of time, or till this point of the time, everything which we have is still the logic, or still in the logical format only. So after this, once all these steps are completed, so the physical design engineer will kind of develop or realize the logic. That means he will convert that whatever we have in the logical format to the physical format. So first step here involved in this process or in the PD flow is the floor plan. Floor plan. So I think all of you guys know about a macro. So in the Excel, we'll be using a macros. What is macro in Excel? In the macro in the Excel is nothing but some sequence of the steps which we follow in order to achieve one functionality. So whenever we wanted to do some steps repeatedly, we'll kind of develop the macro. So when we develop this macro, it will just click whenever required or wherever required, and it will be kind of function, or it will be kind of loop. So that means we will record that our actions, and a macro will be created. Or in other words, I can say in the C language we have a function. So whenever we want to achieve some specific functionality, we kind of develop the function, and we kind of use that repeatedly whenever required. For example, say adder. So we want to add and we want to add two elements and add two numbers, and produce the output. So we kind of develop a function, C language function, and we can use that whenever required. So that means whenever we wanted to achieve one specific functionality, or whenever we wanted to do something repeatedly, we kind of develop a macro. So similar thing we have in the PD also, or in our ASIC flow, ASIC design also. Let's say we have a RAM. So let's say whose RAM is capable, for example, let's say one RAM is able to store 1 MB of data. So if our specification says that we need 4 MB, so what happens? What we do is we will use 4 such things. So 1, 2, sorry, I'm bad at drawing here, 3 and 4. So we need 4 such. We have instantiated 4 such macros. So now as we have 4 such macros, so here the floor plan means, so let's suppose this is my complete chip. So we need 4 MB of cache, where we need to place this 4 MB of cache. So that is what we call it as the floor plan. So we can say I can say that I have put it over here like this. Sorry, it cannot be overlapped. It cannot be one over another. So I can say this is kind of present like this. So we have placed all these 4 macros here like this. So Placing of these macros in my chip is what we call it as floor planning. So that is what we do in the floor plan, and this is like one of the important step or in the physical design. Most of the tools will take the floor plan as a reference, and its algorithms are based upon that. So that's why I can say the floor planning is like some kind of important step here involved in the PD flow. So after this floor plan, so we have the placement. The placement is nothing but like place. So this is like bigger macros. So again, I also said that in the synthesis step we'll be converting that into gate level netlist. So that means we have like 1 million of transistors in our design. So that means we have many gates which we need to place now on the design. So with our like say manually, if at all we want to place all of them, we can either go mad or we can be doing something wrong, and we cannot kind of have a proper thing. So what we need to do over here, so that's where we'll make use of some of the softwares or PNR tools, we call them either ICC2 or ICC or NOVOS. So all these are like placement PNR tools we call. So with help of these softwares or these tools, we kind of place all our transistors, all our gates in our core area on our chip. This is my chip, my integrator circuit, supposed integrator circuit, and we'll place all of them over here. So I'll just place few of them for you. So the size of that will be very less compared to my macro. So we'll be placing all of them like this over here. So yeah, I'm only placing few of them, but yeah, so this is how it looks like. So we'll be placing all of them over here on my design. So we call this particular step or as a placement. So once the placement is done, maybe all our area will be filled with my placement cells, placement logic gates or all the transistors in the design. So then it comes to my CTS. So before going to or discussing in depth about the CTS stage, I wanted to say like what is a memory element? What is a memory element? The memory element you might have known about the D flip-flop or any flip-flops or latches. So all these, these flops or latches will kind of store the data inside that. So because for example, we wanted to achieve one's functionality, so based upon the number of gates involved in that, or based upon the number of gates we have in order to achieve that functionality, so we can say the time is dependent. That means, for example, um, we need some, for example, let's say we need some 4 gates to form one functionality. So some of them like might require some 5 gates, or some of them might require like 6 gates or 7 gates, so on and so forth. So what I'm trying to say here is like uh, we kind of need some of the gates in order to achieve my functionality. So uh, that means like we kind of need to store the data intermediately. So for example, say we are providing some of the input over here and we need to achieve some of the output over here. So in between what we place is what? We'll place some of the memory elements. Let's say we have placed some of the let's say 3 memory elements which we have here. Let's say we have 3 memory elements placed like this. So from first element it's going to the first flop, D flip flop, let's say most common one which we use, and then it's going to the next element, next flop, D flip flop, and next third flip flop, and from here it's going to my output. So we kind of need this because we need to store the element, we need to store the data present here, and so once some person is providing the input, we can excuse me, we kind of need to store in the first memory element, and then we'll start processing that, and then it is going to the next state, and the next state is nothing but one second flip-flop, and from that, based upon some of the processing, it is going to the third state, and from this third state it is going to the output. So that means like now we have the 3 stages and we have the three memory elements here. So D flip-flop or this one is basically operated on the clock. So clock is the one of the input which we have to the D flip-flop. So or any kind of memory element of flip-flops. So based upon whenever the clock is reaching or the rising edge reaches this D flip-flop, it kind of captures the data and stores inside it, stores inside these flops. So whenever the clock rise edge reaches these flops, it starts working. It kind of stores whatever is present on the input, and it will be storing that, and it will be propagating onto the Q pin forever till the next clock edge receives. So that means now, as I said to you this, so now in order to provide this input and in order to see the output, now we require 3 cycles. That means from the first cycle, the data reaches here, and the next cycle, the data reaches here, and third cycle data reaches here, and then it is going to my output. So that means we need 3 cycles over here in order to propagate the data, in order to take the data from the input, process it, and give it to the output. If at all we are having this kind of data with us, we can say after how much time, we can say, like say the data is present or available to us, and when we can expect the output. So we kind of have that information with us. So when we use this D flip-flops and all the memory elements, we can say our environment is synchronous. So we don't want any kind of asynchronous signals or elements signals in my design, because when we have this asynchronous designs, asynchronous signals, uh, whose functionality or whose behavior we cannot expect. So if at all we have that asynchronous signals, our life will become very much complex. So because we cannot deal with all the various kind of asynchronous signals. So because it's not only one such functionality, one such path we have. We'll be having multiple such things in my design. So in order to deal with all of them, it will become quite tough, and that's the reason we want everything in our design to be synchronous. So based upon the clock element, based upon the clock signal, it reacts, it will kind of store the data, and it then propagates the data to the next step. So as we have this one, so that means now you can imagine how the clock, what is the important role we have for the clock here in our designs. So all our designs is like all our memory elements is based upon the clock, and that's the reason the clock signal is kind of important for us. So let's suppose we have a clock signal whose clock period is 1 minute, let's say. So the clock signal looks like this. So that means from the first rising edge to the next rising edge, the time which it has taken is 1 minute. So and from here again to the next rising edge, let's say it is 1 more minute. That means once we have provided the input, in order to see the output here, we need now 3 minutes. So just taking some practical example, practical time units, that's minutes. 3 minutes we need from in order to reach from here to here. So it's 3 minutes when clock is provided at the same time to all these three memory elements. Let's say for some reason, because like say this is nearer to the source, for example clock is coming from here, clock signal is coming from here, so clock will reach this flop faster compared to this one. The guy sitting over here will receive the clock after some time compared to the flop compared to the guy sitting over here. So that means we kind of have some difference over here. So if we have only three elements in our design, we are seeing or we can sense the difference. But imagine if we have, like say, some millions of memory elements present in our design, how complex it will be to manage all of them. So let's say, so this guy has received the clock and this guy starts working, and then So we will expect that this data needs to be stored in the next memory element after some time, right? So if this guy kind of receives the clock signal late, or if at all this guy receives the clock signal early, so I can say it's like we have something missing over here. So for example, say how in the layman words I can say, uh, how can I, yeah, because like say the kind of the insertion delay which we have, we call that the time taken for the data, for the signal to reach from the clock source to its to the memory elements, we call it as the insertion delay. So we wanted to maintain that insertion delay constant in all of them. So that's the reason, like say we kind of need one separate step, which is nothing but the CTS. So as part of the CTS, what we will do is we kind of ensure that the clock signal is reaching all the memory elements at the same time. So all the clock signal will reach to all the memory elements present in my design at the same time. That's our aim of the CTS. CTS is nothing but clock tree synthesis. So with the help of CTS, we kind of achieve this kind of uh, like target here. So we'll do that CTS. We kind of provide clock signal to all of them at the same time. So then we'll move on to the next step, which is nothing but routing. So routing, here routing in the sense, so far we are saying that communication is present from here to here. So it's only logical. So in order to connect this output pin to this input pin, what we need to have? We need to have some physical connections, right? So that is with the help of the metal shapes. So with the help of the metal shapes, we will connect its output pin to its input pin. So most of the cases, these metals are nothing but the coppers. Some of the cases like where the resistivity matters, we'll be kind of using the gold also. But most of the cases will be using the copper. So we'll be kind of we're using one metal shape, one metal piece, and then connect from output pin to the input pin with that metal shape. So when we do that, what happens is now we can say the physical connections is also formed. Till the routing stage, I can say there is no physical communication or physical connection. After this routing, I can say the physical connection is now formed over here. So we are kind of connecting one metal shape to the other metal shape, and now I can say the routing is done. And with the routing, with this one, we can we say we have realized that logic completely. That means whatever is present in the logical format, we have converted that to the physical format altogether till this routing stage. So but now as I said to you, as I mean everything needs to be verified. So same that is what we have one of the important step, sign off. So in the sign off step, we kind of test whatever we have achieved, or whatever we kind of converted that logical thing to physical format, or we have realized that logic or not. We will be kind of checking, we'll be having multiple or various kind of checks in order to scrutinize that, in order to get that confirmation. We'll be doing that at this kind of step, and then we say we can tape out the design. The tape out is like the process of sending the data to the fabrication for the fabrication. So we can kind of do the tape out, and with this with the work of the PD engineer will finish. So once that is done, the tape out is done, and the data is being sent to the foundry for fabrication. So the fabrication, some of the steps involved in the fabrication, it will be involved and it will be done, and it is fabricated and IC will be out. So as I said to you, the packaging and testing team will be there. So I mean in the process, in the fabrication itself, the DFT, the logic whichever we have used will be used here, and it will be tested, and whatever is working it will be shipped, and other one will be discarded throughout there itself. So and then we'll be sending that to the packaging and testing team. Packaging is nothing but like if at all you have seen the fabric in the IC, so it will be inside one package. It will be either in the ceramic package, or it will be either in the plastic package. So Nowadays, like we are using the plastic packages, and this packages is kind of sealed. That means like it's airtight, and we kind of not allow any of the dust particles or nothing to go inside this particular chip, because if at all even a tiny teenage dust particle is present or entered into that, the functionality of it will be disturbed, and it will be completely damaging that chip. So the packaging is pretty much important and very important. And after this packaging, so we can only see the outputs. Like say, we can kind of see some of the bond pads or some of the pins, so with which we can communicate with our IC integrated circuit, which is fabricated, or our silicon, which is present inside my package. So after this, like we'll be having the testing team. So the testing team will rigorously check the performance of this particular guy. So we have developed this particular one according to some specifications, and if so we are be able to achieve, or we have achieved that particular testing or that functionality or not. We'll be having this guy. We'll be doing over here. So you might have seen some of the jobs, like the person who wants to who wants to play games from day in to day out. So that means like say why one has to hire a person to play the games, because so when this one, as soon as any of the chip is fabricated, it will be straight away going to these guys, and they will be playing the games, and in the background we'll be doing, or we'll be running some of the performance checks. So it will kind of evaluate how much is what is the performance of our design, or what is the performance of the chip which we have fabricated, what is that we are thinking, or what is that we thought we have in our mind, did we realize that or not, and what is the performance benchmarks we have. So we'll be kind of testing it by playing it, or by doing many other checks. So that's what, like say, that's what happens in the packaging, and after packaging and testing. So after all these steps, we have one thing in our hand, that is a chip. So which is being shipped to the customers, and at the end, the happy customers will take that, will insert it in our mobile processors or laptops, and then he will use it for his day-to-day activities. So this is like our complete application specific integrated circuit flow. And at the end of this flow, we have one chip in our hand. Okay, let's move on to the importance of the physical design engineer. So as I said to you, aim of any PD engineer, physical design engineer, is to realize the logic. So he is kind of converting that logical format thing to the physical format. So time to market plays an important role in the VLSI industry, and PD engineer plays a crucial role here in this project, in this aspect. For example, if any of the person has done the mistake, so because that is kind of burden to the physical design engineer, because if something needs to be changed in the logic, PD engineer has to do all the things again from starting. He has to do the flow plan, placement, and everything again. That means like if some mistake is there in the from any person on the top, that PD engineer has to be should be in a position to take that, incorporate it, and still we need to give, or we need to deliver the project on time. So the person PD engineer is the one who is going to do all the kind of sign off checks, and will be kind of doing the tape out. So this is the guy. This is the last step in our fabrication, or in the designing part. Now if at all in person has done any kind of mistakes, like PJ engineer is the one obvious person who is going to be responsible for that, because time to market is very important. Because for example, say we have like say back to school days. So when we have some back to school days, so we want all our latest chips on board in available, readily available on the market. So that means like, so this is the time when most of the parents or students will think to kind of buy new gadgets, or kind of buy new things, which new accessories required for his study or anything. So he'll be kind of buying that gadgets, and he'll be keeping it handy, and he'll be using that. So if at all we miss that particular time slot, if at all we don't have our product in the market at that time, so when every person is trying to buy, so then it's a huge business loss. Even if we have developed a little 1 month delayed or 2 months delayed or 15 days delayed, also we can kind of lose a market share, significant market share. That means we don't have any customer to buy our product, and that's a huge loss. So that's the reason. So the time to market plays an important or crucial role, and field engineer has to be plays a significant or prominent role because of the said factors before. So responsible for delivering data to the various stakeholders. So this person, he is like kind of should give or deliver the required data to various stakeholders, like whatever it may be, packaging team or other stakeholders which we have. So he's the person who is going to communicate with the various guys in the project. So responsible for multiple sign-off checks to make the design tape out ready. As I said, you tape out in the sense the process of sending, doing the necessary checks and sending the data to the foundry for fabrication. So he should do various sign-off checks and make the design tape out ready. So that's how that's what the importance of the physical design engineer is. So now I just want to take you through some of the latest trends in the lower technology node. So the one such thing is MBCFET. So the multiple channel field effect transistor. So this is from the Samsung. So instead of using the nanowires or the fins like this, so he kind of using the stacked things. So where nanowires, this is like nothing but gate all around structure, but the nanowires are now converted to the nano sheets. So this is a nano sheet here which we have, and this is from the Samsung foundry. So it's like gate all around, but instead of using the nanowires, we kind of using the nano sheets here. So this is the latest advancement which we have. The next one is the 3D chip. So majority or most of the time we kind of have like say multiple we may need multiple processors on the motherboard, and we need to have the communication from one die to the other die. So instead of having two different processor on the motherboard and kind of enabling them through the motherboard, so why can't we have one chip over the other? That means 3D architecture. So we have one chip on the top and other chip on the bottom. So that means, so this is like kind of 3D chip. So if at all there is kind of we have any kind of communication from one die to other die or one chip to other chip, we can make use of the TSV, which is nothing but through silicon via. With the help of through silicon via, we kind of enable communication from one die to other die in the help of TSVs. So accessing a processor by the peripherals will become easier with this kind of approach, because now it need not to go all the way through some of the channels on the motherboard or whatever it is. So that means if at all we are having any kind of communication from one die to other die, so it's kind of it will become easier. So that is what I want to say as part of this 3D chip. So this is one of the latest trend which we have in the lower technology nodes. So monolithic 3D chip, I will discuss it in the next slides. So case studies. So I just want to put in front of you some of the case studies which we have. The first one is the self-gated register. So reducing switching power or dynamic power consumption is one of the important tasks of any physical design engineer. So we kind of enable or we kind of develop our chip with as much minimal power consumption as possible. So in order to do that, we can kind of use the clock gator to reduce the switching power, because the clock is the one signal which is constantly switching from 0 to 1, 0 to 1. It's the clock signal will switch forever. So that means like majority of the switching power whatever we have is because of the clock signal. Whenever we don't need some part of the design to work, so we kind of disable the clock to that. That means the switching will be kind of reduced. So we can kind of disable that with the help of the clock gators. So, but even more effective is to use the self-gated register. So self-gated register is nothing but, so based upon, for example, we are having some clock and we have the input and we have the output. So we have the clock signal like this over here. So whenever the output changes, whenever the input is changed, okay, only then we need to store the data. So in our digital world, what we have only 0 or 1. So we have only 0 or 1 is what we deal with in our digital world. So 0, for example, this data 0 is the one which is stored here. So for the next clock signal, if the input is still 0, do you think that we need to give the clock signal to this guy and store the data? No, because already 0 is stored. So what we'll do is we'll kind of compare input and output. So we'll compare whatever is present on the output with the input. If there is any change, only then we'll provide the clock signal to this guy. So then the kind of, we can, with the help of this, we kind of reduce the switching activity, and is very much better or better way to do that. But it has its own complexities. It's only one kind of case study. It has to be implemented. It has to be tested in various designs, and it will take some time to realize this or make use this in our integrator circuits. So the next one is the triple patterning. So as the technology node is shrinking, so for example, we are having earlier we might be having a chip, or we might be having a metal with this much thick. But as the technology node is shrinking, what happens is that the size or the width of it might shrink even further. So it can become like this, or even if at all we go to the lower technology node, it can be like a just simple line like this. That means like the width of the gates, or width of the metals which we use is kind of reduced. So that means like it says that the fabrication it has become like pretty much tough. So the UV light frequency is like is something. So if we wanted to fabricate this larger width, so it might be easy, because for example, say whenever you pass the UV light, because of its properties like diffraction, so instead of light falling on one particular area, so I can say it can, for example, instead of spreading to this particular area, it can now spread like some more area than expected. So now if the width of this is reducing, so if whatever may be the UV light frequency which you use, we kind of still have that loss, and then because of its light, because of the property of the light, we cannot kind of fabricate it as expected. So so far we are using the double patterning, but now going forward, so as the technology node is shrinking, so we kind of use the triple patterning also. So in order to fabricate one layer, now we will use three different kind of mask. So for fabricating one shape, kind of use three different masks now. So that is what nothing but the triple patterning. So monolithic 3D chip. So in the 3D chip, the resistance offered by the TSVs are more. So instead of fabricating two chips and connecting them using TSVs, we can form two active device layers. That means we can kind of form two different transistors on one chip, one above the other, and now so we can eliminate the usage of the TSVs also. That means both of the transistors are on one chip. That means one above the other we have two transistors. So that is what nothing but my monolithic 3D chip, and it has a lot of fabrication complexities involved, and it takes some time to. And the last slide for today or for now is the job opportunities one can have. So one can choose one of the following roles, like front-end engineer, verification engineer, physical design engineer, or the DFT engineer. So the front-end engineer is kind of developing the logic. So with the help of Etlog or some other tools, the verification engineer is going to test the logic which is developed by the front-end guy, and then the physical design engineer is going to realize that logic, and the DFT guy is going to uh, enable the process of testing once the chip is fabricated. So these guys are, I mean, these are the some of the important roles that you can have as part of, I mean, if at all you wanted to be in the VLSI industry. So these are some of the companies which we have, the product-based companies, some of the startup companies, and some of the service-based companies and tool-based companies. The tool guys are the ones who are going to provide our softwares in order to help doing our respective tasks by these guys, front end verification, physical design, or DFT guys. So like so, yeah, we have. I'm just flash you some of the known or like some of the companies which are out there in the market, but we have several other companies in the market. And yeah, we have, like, say, I mean, I can say the opportunity or the field is very narrow compared to software which is widespread. The opportunities which we have is very narrow, but yeah, we have significant number of companies now in the nowadays. I mean, the size of the companies is growing, or the count of the companies is growing. With this, I just want to conclude, and yeah, thank you very much, guys, for having gone through my complete video. And I hope this will kind of help you guys in deciding or having or getting an overview of what is VLSI. Thank you, guys. This is Prashant signing off.